Okay. Okay, great. All right, so I usually do have a loud voice, but I am a little tired of talking this week after 24 hours of teaching. I taught our resident. I don't know if you were here when I said that. I taught our residents this week.
Oh, you did?
Yeah, and I teach Monday, Tuesday, and Wednesday, 8 hours.
Oh my gosh.
So I'm a little tired. But good news, the lectures are fresh. All right, we ready? Okay. All right, so these are some key components, things that I think are important to know. So proton, neutron, and electron. In terms of, committing all of this to memory, I think it's really hard to remember, the rest mass in kilograms, but I think easily rememberable are the rest mass in MeV, right? So rest mass of proton and neutron are almost the same, 938 and 940. And then for an electron, it's 0.511 MeV, right? And then the unit charge, that is actually important, but you're going to hear it so many times in the lectures, you'll probably have it memorized by the end of today. So 1.6 times 10 to the minus 19 coulombs for the proton, and then the negative of that for the electron, negative 1.6 times 10 to the minus 19. In terms of stability, the proton and neutron are stable. The neutron inside of the nucleus, unstable is free, meaning that when it's outside of the nucleus, it very quickly reacts, right? And so we'll talk a little bit about neutrons later because it's my hobby. And then electrons, stable. And then keep in mind there's also, sometimes it'll be called the beta minus particle, and its antiparticle is the beta plus particle. So analogous, same weight, but positive charge instead of negative charge. Okay, nuclear structure. Oh, some trivia in terms of the nucleus being about 2 times more massive than electrons. And then I think the important key concept is that the nucleus, the same way that you have electronic orbitals that have that fine structure where you have a set of shells that have energies associated with that, so does the nucleus. And it'll come into play in our next lecture when we talk about gamma decay. So I'm gonna use this throughout the next lecture when we talk about the modes of radioactive decay. So atomic number will be denoted with the Z, and that tells you the number of protons in the nucleus. Mass being the number of neutrons plus the number of protons. N just being the neutron number, right? So A minus Z. And then a nuclide is any species of an atomic nucleus with a specific A and a specific Z. And then this is the nomenclature that I'll use throughout the lecture. A, Z, and N, and then you can always figure out N from the other. And categories, nuclide categories, so isotopes. And so I put in red sort of, the things that are the same. So isotopes have the same number of protons, and that also makes them of the same element, so they have the same chemical properties, but their nuclear properties will be different. Isotones, nuclides that have the same N number but different A. Isobars, all nuclides have the same A but different Z. And isomers, everything's the same except the energy level. Okay, nuclear stability. So there's some interesting trends in terms of number of protons and number of neutrons. So stable elements in the low atomic number range all have almost equal numbers of protons and neutrons. But then as the number of protons increases above about 20, the neutron to proton ratio for stable nuclei becomes greater than 1. And in terms of just thinking about that and does it make sense, right? If you have a lot of protons in the nucleus, they're repelling each other through Coulomb forces, and so those neutrons, the extra neutrons, add some space and distance and help stabilize the nucleus. Even in odd numbers, so over half of the stable isotopes have even numbers of protons and even numbers of neutrons. And so this suggests that even is stable since the majority have that configuration. Only 4 stable nuclei have both odd Z and odd N, right? So suggesting that that's unstable. And then the rest sort of fit into mix match, right? So you might have even Z and odd N, or odd N and even Z, and that falls into about 20%. So just in terms of trends in data, if you're looking at a collection of isotopes, right? So if you see even, stable, odd, unstable, then the others will fall somewhere in the middle, and you can sort of use that information to predict if you were looking at a list of isotopes, what's stable and what's not. All right, so then elements that have any Many elements can have multiple stable isotopes. Some have as many as 10 stable isotopes. Elements with Z greater than 82 have isotopes that are known to undergo radioactive decay. And as an example of an element with multiple isotopes, deuteron and tritium. All right, so switching gear to basic energy units, joule equal to the work done when 1 force of a Newton acts through a distance of 1 meter. Not particularly relevant to radiation therapy, but the electron volt, in fact, is quite relevant. And this is defined as the kinetic energy acquired by an electron in passing through a potential difference of 1 volt. And so really when we're talking about X-ray tubes and how we accelerate electrons, if we have an electron and we put a voltage difference between 2 electrodes, as that electron passes through that voltage difference, it acquires that amount of energy. And so the unit, the electron volt, is a very common unit. And so the electron volt, if you take 1 volt and multiply by the charge of the electron, minus 1.602 times 10 to the minus 19 coulomb, that gives you the unit of joules. So 1 electron volt is equal to this many joules. And then the equivalence of mass and energy, the E equals mc squared. On that first slide, I showed you the mass in kilograms of each of the particles and then the energy, right? So you can use that equation to go back and forth between the mass in kilograms and the energy, the rest mass of the different particles. All right, so atomic mass unit is expressed, it's the mass of an atom expressed in AMU. The gram atomic weight is the mass in grams, and it's numerically equal to the atomic weight, and that's in grams per mole from basic chemistry. And then Avogadro's number, the 6.02 times 10 to the 23rd atoms per mole. And so we're going to do a couple of conversions looking at, for different elements, sort of what these numbers look like when we do some calculations. All right, so the atomic mass and energy units. So here I've derived it. I don't necessarily think that the derivation itself is important, but I think it's always nice to sort of fundamentally look at these things. So if I take an AMU and I say that's equal to 1 gram per mole, and then I know that 1 mole has 6.02 times 10 to the 23rd atoms, and I know that a kilogram has 1,000 grams, and I cancel my units out, you can see that 1 AMU equals this many kilograms. And then I can put that into this equation, right? So the E equals mc squared. So if I take this many kilograms, the kilogram equivalent of 1 AMU, and I multiply by the speed of light and I square that, I get this many joules. And then if I take that number of joules and I do the joule to electron volt conversion, and then I go from MEV or EV to MEV, you see that 1 AMU is equivalent to 931 MEV. So I always like to look at the derivation of units and then commit sort of the final thing to memory, right? So there's not only so much time on exams to do things, but I think looking at that. But now if you know that 1 AMU is 931 MeV, if I asked you how many AMU in a proton or an electron or a neutron, and you know that they're 938 or 940, 938, and 0.511 MeV, you can easily go back and forth without too much effort. And so I did that here on this slide. And then putting it into context, the proton and the neutron, they're about 1,800 to 2,000, depending how you like to do your rounding, more massive, or conversely more energetic than an electron. All right, mass defect. The mass defect, the mass of an atom is not equal exactly to the sum of the constituent particles, right? So if we took the mass difference between the mass of the atom and the sum of each of the individual parts, this would be the mass defect. And so essentially when the nucleus is formed, there's a certain amount of mass that's destroyed and converted into energy. And that sort of acts as the glue or the binding energy to hold those nucleons together. And so if we do a calculation to see what it is, this is an example with carbon-12. And so again, if you have those first couple of numbers memorized, it's really easy, right? So 6 times 938 for 6 neutrons, 6 times 940.
Couple slides back, it
Yeah.
said 930 and
Oh,
940.
there might have been a
Oh,
typo.
there's a typo.
Oh, it's a typo. So correct your slide. Oh, and no one else has noticed that all week.
Oh, we're
Okay,
not sleeping.
You're not sleeping yet. All right, so correct that on your slide, and I'll correct it on my slide deck later. Right, so if I look at those, if I multiply those out and add them together, and then I convert between, I use the 931 to 1 AMU conversion, I see that I have 12.103. But the mass, right, of carbon-12 is 12, so the difference between that is 0.103 AMU. That's the mass defect. But I could also think of that in terms of energy, right? So if I converted that mass defect into energy, that's the binding energy, right? So definition-wise, the energy equivalent of mass defect is the binding energy. And so if we take that same example and we take the 0.103 AMU and we convert that, you see that I have 95.9 MeV. So when a carbon-12 nucleus is formed, you can say that 0.103 AMUs are destroyed and converted into 95.9 MeV of energy, which holds the nucleons together. We can also think of the binding energy in terms of per nucleon. And so the binding energy is a measure essentially of the cohesiveness or the stability of the nucleus. And so if we take the binding energy and just divide by the number of nucleons or the atomic mass, right? So for example, for the carbon-12, I had the 95.9 MeV, and if I divided that by 12, that would sort of give me a way to compare one nucleus to another in terms of how stable it is. So some general trends in terms of binding energy per nucleon. For pretty much every element, it's going to range between 7.5 and 8.8 for all nuclei. Iron 56 has the largest binding energy per nucleon, and it's also the most stable element on the periodic table. The binding energy per nucleon is slightly higher for nuclides in the ground state versus the excited state. Okay, so here's the carbon-12 example, right? So we see that it works out to be 7.99, fitting right into that range of 7.5 to 8.8. And then this is a plot that I actually really like quite a bit. So it's the atomic mass for different elements. So that's the A plotted against the binding energy per nucleon. And so it's the stability sort of increasing, and then as you hit iron 56, with increasing mass, then the stability starts to decrease. And so you could look at different isotopes just based on their binding energy per nucleon and estimate, is it going to be more stable or less stable? And so in terms of its stability, what does that mean? Is it likely to, what type of interaction is it likely to undergo? And so if we're talking about in the low Z, low atomic mass, you're more likely to have a fusion type. And then when the stability decreases on the other end, you're more likely to have a fission, right? So big isotopes are likely to break apart. Small isotopes are likely to bind with others. Okay. Oh, I thought I took these out. We'll skip these, and I wanted to discuss this here. So this is the effect of Z and A on various quantities of interest. And these quantities of interest are going to come into play when we talk about things like Compton interaction and probabilities and other things. So I want to walk through some examples. But if we wanted to calculate atoms per gram, that's Avogadro's number over the atomic weight. If we wanted to do the inverse, grams per atom, we just flip that. And then electrons per gram, which is a particularly important quantity because it relates to the probability of a Compton interaction. So that's going to be Avogadro's number times Z over A. And then if I wanted to just calculate the electrons per centimeter squared, I take the electrons per gram and I'm going to multiply by the physical density. And so here I've worked through some examples for you for carbon and lead just to compare them. So if we look at the atoms per gram, oh, and so I should mention this. So the Z for carbon is 6. And I had to pick A density, so I picked the one for graphite, which is one of the most common forms of carbon. And then for lead, 82, and then its physical density, you can see, is almost 5 times larger, right? So if we look at atoms per gram, and I go through, and here I've kept the units, so you can see how everything cancels. I end up with 5 times 10 to the 22nd for carbon, And for lead, I end up with a smaller number of 2.91, right? And so even though it's a larger, heavier isotope, the atoms per gram is actually lower. And then if I look at grams per atom, you see the opposite effect. And then electrons per gram, which is particularly important, you notice they're really not all that different between these two materials. So one is 3.01 times 10 to the 23rd, and the other is 2.38. So despite their huge difference in Z and density, there's just not that much difference in the number of electrons per gram. And then if we multiply by the densities, then we see a bigger effect, right? So, but I think one of the key things is, sort of looking at different elements and really seeing that there's not that much difference there. Okay. And so, and why does that happen? And so the Avogadro's number is a constant, so it's really the Z over A component of that equation. And so for almost all elements, the Z over A is essentially constant from about 0.4 to 0.5, with the exception, obviously, of hydrogen, because hydrogen's going to be 1. And so when we talk about photon interactions and the likelihood of a photon interaction, this is going to have a big effect. So, all right. Atomic structure. So most of you have probably taken way more chemistry than you've wanted to in your lifetime, so I won't go over this in detail. Right, but so the electrons are going to be organized into different shells, and the number of protons is equal to the number of electrons in a neutral element. And let's see, not sure how much I want to say. So I want to talk a little bit about the number of electrons in the outer shell, right? So in the outer shell, the maximum number of electrons is 8, and that's because you have those S and P orbitals. But the total maximum number of electrons in any orbital is 2n squared. So, for example, if we look at the in column 8 of the periodic table, or the inert gases, aside from helium, which only has 2, here's the electron configuration, right? So for all, the outer shell is always 2 or S2 and P6 in terms of those orbitals. And then here, what I've denoted is this is the isotope before it. So it has all the same configurations as helium, and then it also has this, same as neon, and then also all of these electrons. And let's see, other things I want to mention. So we just talked about binding energy of nucleons, binding energy for electrons. So the binding energy for of an electron in an atom is the minimum energy required to remove the electron from the atom, or it's a measure of how tightly that electron is bound to it. And this is going to depend on the magnitude of the Coulomb force between the nucleons and the orbital electrons. And so if you have a higher Z, or the binding energy for an electron is much higher for large atoms, right? Because you have higher Z, and so if you have a higher Z, that means you have more protons, so there's greater nuclear charge. And it's going to decrease with increasing shell number, meaning if I have an electron, say in the K shell that's very close to the nucleus, that's going to be much more tightly bound than an electron that's in an L shell or an M shell. The farther you get away, the less that attraction of the Coulomb force between the nucleons and the electrons. And then ionization and excitation, right? So ionization is removing an orbital electron, and excitation is exciting it to a higher energy level. And we are going to spend a lot of time talking about these, so this slide is just so that you have just the facts, like the absolute definitions of these, and then in, I think it's the third lecture, we'll spend a lot of time on this. All right, nuclear forces. I feel like these are trivia mostly. I won't spend too much time on them, so there's 4. There's the strong nuclear force, the electromagnetic force, the weak force, and the gravitational force. And so in terms of their strength, they go in decreasing order from the first one to the last one. That's really all I'll say about those. You can read them, that slide. And then nuclear energy levels, I've already talked about this. It's very similar to the electron energy levels. And I think this is the last subject in this lecture, the electromagnetic radiation and the principle of the wave model, right? So An electromagnetic wave can be represented by spatial variations in intensities of an electric field and a magnetic field.